Okay, guys, welcome back. This is the end of our third week. 5 more to go. Yeah. Okay. I sent an email concerning the next exam. I pushed it uh, to Thursday for next week rather than Tuesday, simply because we were still on chapter 5, which we'll knock out today, and then I'll jump into 6. Probably finish that on Tuesday. Okay. And next Tuesday will be 6, 7. So as I stated in the beginning, with respect to the syllabus, our due dates will be shifted accordingly depending on how we progress. Sometimes I have to uh, spend a little extra time in certain chapters based on the questions and so forth. So we'll adjust accordingly. Again, if there is another assignment that I've not moved, remember, it will not be, any assignment won't be due until, with respect to the lecture part, until after we complete that chapter. So if there's a homework, let's say homework 5 due today, well, obviously that won't be the case and have time yet to move it. Okay. So, okay. I got everything graded for the last exam. Average was, I believe, 80s, so wasn't too bad. Let's see. Trying to think of some other things that we need to go over before I proceed. No. Can anybody have any questions, comments, concerns? No? Okay, well, let us continue then. Now, what we've done at this point, up to this point, we've talked about, the subatomic particles with respect to protons and the neutrons, determine that they are in the center of the atom, and then the electrons are orbiting someplace somehow around the atom. This chapter gives you more specific information that the electrons are treated as wave particles and do in fact act as wave particles and have wave properties. We found out that elements that were excited emitted light due to the excitement of the amount of energy at specific wavelengths, which tells us that these electrons were being excited to specific energy levels. And hence we got into energy levels that the electrons occupy. Okay. We have 7 energy levels. The periodic table, if you go across the periodic table, there are 7, what we call the horizontal columns, if you will. There are 7 of them, which represent the 7 energy levels that we have to date for the 118 elements that we have. Eventually, when we get above that, we're going to introduce more energy levels. Then the model came out that there are 4 types of sublevels within the energy levels. These sublevels are called orbits. Orbits in which the electrons occupy. There are 4 types of orbits that have been given letters, and those are the S, the P, the D, and the F with respect to the type of orbits. We determined that there are mathematically, that is, because it's all based on the mathematical models, and that being the case, the experimental models verify that to a large extent, that we're in the right track, but are we 100%? Yeah, somewhat. Okay. And so there's 1 S orbital. And then for the P's, there are 3 P orbitals, and there are 5 D as in Delta orbitals, and 7 F orbitals. Now, each orbital has a maximum of 2 electrons. Therefore, the S orbitals, having only 1 S, can occupy a total of 2 electrons for all the S orbitals. The P's, there are 3 orbitals, and each one can have 2 electrons. So there's a total of 6 electrons that the maximum number of electrons for the P orbitals is 6. For the D, there are 5 orbitals, and each one can capable of handling 2 electrons. So we have a total of 10 electrons maximum that we can place in the d orbitals, and finally, 7 orbitals for the f orbitals, and two electrons for each one, giving us a maximum of 14 electrons in for the f orbitals. We talked about a sequence when we fill these orbits up with electrons. We start at the most the lower energy level, which is the first period. And then we start off with 1s, 2s, 2p, 3s, 3p, 4s, etc., shown here in that diagram down the bottom, written in blue. That is the level in which the orbits are filled with electrons. You fill the s first, then the p, then the d, and then the f. Remember, the number in front of the orbit letter is the energy level, the coefficient. So 1 represents the first energy level, 2 represents the second, and so forth until you get to the 7th energy level. Let me step back one more. We had in the first energy level, we have only one orbit, and this diagram demonstrates that. That box represents the s orbit. There's only one. We're not talking about the shape here, it's just that there's one orbit, and that one orbit can handle 2 electrons. So in that box, we can put 2 electrons for the first level. And in the second level, keeping in mind the periodic table, when we move down to the second energy level, the second period, the horizontal columns, we have 2 types of suborbits, the s and the p. Okay, again, each box can handle 2 electrons. The third energy level, okay, we have introduced the d orbits. Okay, and the fourth energy level, the f orbits come into play. Each box again represents 2 electrons. So to reemphasize a point is this: the s can handle 2 max, p's can handle 6 max electrons, d a max of 10, and f a max of 14 for the orbits themselves. Now, but the energy levels have a different number. And so looking at this diagram, can somebody tell me what is the maximum number of electrons that you can place in the second energy level? What is the maximum number of electrons? What do we got here? All right, exactly 8, okay? Because we can put 6 in the P and 2 in the S in the second energy level, giving us a total of 8 electrons for the second energy level. What about the third energy level? Okay. What is the maximum number of electrons that we can put in the third energy level? And 18, and that is correct. Okay, because the D can handle 10. The P can handle a total of 6, and then 2 for the S, so giving us a total of 18. And so if you ever ask the question, the maximum number of electrons, read the question carefully. Are they talking about the orbital itself, or are they talking about the energy level? Okay, so there is a difference there. Let me just give you a heads up. And this was, again, as I explained, that these orbitals, or orbits, either one, the S, the P, the D, and the F, is the result of mathematical equations, and these three-dimensional mathematical equations. And that being the case, data can be plotted to these equations, and you end up with an image for the S given like as this. It represents a round sphere, okay? And in that colored area is what is described as the probability of an electron being in a certain area. The P's being three dimension, okay? We deal with 3 dimensions, there are 3 P's. And those are the shapes of the mathematical equations that represent the P orbits. And the D's are very complicated. I stated you may want to go do a search on the internet for D and F orbits to get images, and you're going to find some really crazy looking orbits. but that's our model. So then we ended up here almost, one more slide, where this represents how to fill the electrons and to write what's called the electron configuration, which describes all the electrons for the element and where they are with respect to the energy level and their orbit. Now, you're welcome to memorize or look at this table, or just use the periodic table and the position of the element to tell you how to write the electron configuration. And I'll show you how to do that here in a little bit. So to rehash the electron configuration, the coefficient, the number 1 through 7 represents the energy level. Then you have the letter S, P, D, and F, which represents the orbit, which type of orbit. And then the superscript on the letter represents the number of electrons in that orbit. So if we were to show 1s superscript 1, that tells you first energy level, first orbit S, 1 electron on that orbit, okay? And if we were to take the, or do the electron configuration for carbon, we know that carbon has a total 6 electrons, okay? And 6 electrons, and we can write its electron configuration as 1s2, because of those 6, the first 2 are going to occupy the first energy level. We're starting to fill up the energy, start from the lowest and work your way out. So 2 electrons in the 1s orbit, and then 2 electrons in the 2s orbit, and then the remaining 2 electrons we have a room for in the p's for 6, but we only have 2 we got to worry about. Fill up the S and then move on to the P. So the electron configuration for carbon will be as written: 1s2, 2s2, 2p2. Okay. Now, remember, the number represents the energy level. And if we look at this electron configuration, we can at a glance determine the number of what is called the valence electrons. The valence electrons are those electrons for any atom that occupy the outermost shell, okay? Because again, that is where all the actions happen. That's where all the chemistry occurs, in the outermost shell. And if we look at carbon right here, we can see that the 2 energy level represents the outermost shell. That is the valence shell. Carbon, as we stated, has 6 total electrons. 4 of them, 4 electrons are in the outermost shell, okay? Of those 4, 2 of them occupy the 2s orbit, and 2 of them occupy the 2p orbit, okay? Outermost shell. The other aspect is this. Carbon, when we find its position in our periodic table, find carbon, element number 6, and that whole column has this number, Roman numeral 4a. That represents the number of valence electrons for that group. Everybody in that group has 4 valence electrons. Okay, for carbon, those 4 valence electrons are in the second energy. All right. Then we did talk about this one here. Again, the boxes represent the number of electrons at different energy levels, 2 electrons per box. Now, if we look at the periodic table is placed in the position such that the atoms are, such that we can relate the energy levels to their position on the periodic table, okay? The first 2 columns at the far left, we can designate those as the S atoms, S as in Sam, okay? And now, guess what? There's 2 columns, column 1 and column 2. All right. Now we move into the red color, and those we can designate as D, the delta elements. And more so, I should say, furthermore, there are 10 columns here. 10 columns in the D elements. There are 2 columns in the S element section. And if we shoot across to the P, all of them in yellow, okay, there are a total of 6 columns. And then down at the bottom, the F elements, there are a total of 14 columns. And so going across the product table, we can go 1S1 in the first column, 1S2 in the second column. We shoot across, well, let me clear here for a second. And then I got another drawing that we like here. And so we can go for these guys right here, for hydrogen, we go 1S1 and we shoot across to helium, 1S2. For lithium, we're in the second energy level, we go 2S2, 1. And then for beryllium, 2S2. And then we hit boron. We're still in the second energy level. 2P1 and go all the way across to neon 2P6, okay? And again, the superscript is the number of electrons. So knowing their position in the product table, we can very quickly write the electron configuration. Now, only when we reach number 21, scanning right here, do we have to worry about the d orbits, okay? And so if we go back to that graph that we showed you, this right here, notice that the d orbits here comes right after 4s. So you got 3d. But you don't have to worry about the d orbits until you reach, if you ever reach number 21, which is scandium, okay? And if you ever go to that position, then this will be 3D1. Now you might say, well, wait a minute. Why is it 3D? Okay. And if you go across all the way to zinc, we can put that as 3DN for zinc. But the question is, why is the coefficient 3? Though the element themselves is in the 4th period. And I'll tell you this. The d orbits with respect to their energy level don't come out where it was anticipated to be, in this case, the 4th energy level. Let's talk about number 21 just for an example. Okay, so when it got to 21, those electron, that extra electron, the next one, because up to electron 20, everything was taken care of, okay? Up to 20, those electrons were in the 4s2, but we got one more electron. Having that one more electron, which is element number 21, that electron can't occupy the s orbit because it's full. And it can't occupy the p because there's not enough electrons to go way over here to the one after zinc, okay? So it occupies the d orbits. And what's happened is the mathematical calculations show that the d orbits actually, from a perspective of energy, are not in the energy level that the atom belongs to. Okay, they are in one number. They are in one energy level. And that is why number 21 for the d elements, the energy level starts with the 3rd period. So it's 3d1. And so for the energy level of any of the d elements, you find the period it's in and just subtract 1, okay? For example, this one right here would be 4d1, okay? It's in the 5th period, but it goes in 1 energy level, okay? Now, along those lines, we get to the F elements. The thing to remember about these F elements is, as in the case where the D, where it was the energy level was 1 minus the period it was in, the energy level. For the F, it is the energy level it's in minus 2. Okay. And so if we look at the here, the level here, the F's, they come into play in the 4th energy level. Okay, the F's come into play in the 4th energy level. But you don't have to worry about it until you get to element number 58, which is this one right here. And then at this point, even though this is in the 6th period and then 7th period, because remember, here's number 58, it fits in here. And I'm going to show you a periodic table when we take those two, the F elements, and we put it inside where it belongs. So you'll see that that periodic table actually stretches out. What has been done is those two in the bottom get pulled down, and we shrink in the periodic table so we can see it a little bit better. And so here, this guy will be, with respect to the F electrons, would be 4F1, that first column, all the way to 4F14 with respect to electrons. Now I have another slide that shows this much better than my handwriting here. Okay. And so for the d orbits, they come out with respect to the energy, one energy lower than where they exist, the elements. And for the F's, their energy level for the S are 2 energy levels less than where they are on the periodic table. Okay. And so the next one down here, the one below this would be 5F1 and go all the way across to 5F14. Okay. And along those lines, where we got 3D1, 5D1, this would be 6D1. Okay. And so on down the road. All right. Now, if we were working with 21, like I was showing you earlier, that electron number 21 electron would be in 3D1. And then we go across the periodic table all the way to zinc, we'll go 3D4, 10, excuse me. Now, once we get into number 31, which is right here, we're back to the P's, and we keep it in the same energy level. So there'd be 4P1 all the way to 4P6. Okay. Clear as mud right now, right? Okay. I have another table where clear this up a little bit. All right. Now, let's do the electron configuration for these particular elements. Okay, so I put the same periodic table with the color periodic table up there. All right, so what we want to do is do sodium. So sodium, recognize where sodium's at first. Okay, let me color this up a little bit so we know where we're at. And so, looking for sodium, sodium is right there. Boom. Okay. And so using the periodic table, I recognize that I'm at the 1, 2, and 3rd energy level for sodium. It occupies the 3rd energy level. Okay. And I only have to worry about 11 electrons. We're dealing with 11 electrons. So that being the case, starting from the beginning, number 1, it's 1s2, and then this fills up the first 2 electrons, 1s2. Okay. Now we got to fill up electron number 3. Well, electron number 3, we can't do any more electrons in the first energy level. Remember, there's only 1 orbit, and that 1 orbit is full now with 2 electrons. So we have to go to the next energy level, which is the second energy level, okay? So that being the case, we start off across the second period of the periodic table. And so going across, we fill up 2 electrons. We know again, s orbit can only handle 2 electrons. And we shoot across all the way across the 6 columns. That fills that up, okay? Finally, and if you count those electrons, count the superscripts, there's 10, but we got one more, okay? And one more is where sodium occupies with respect to its energy level, which is the third, and it is in the first column, which is the S atoms, right? And so I just need to go to 3s1. See that? 1s2, 2p2, 2p6, and then 3s1. Now, how many valence electrons does sodium have? Exactly 1. 1 valence electrons, and that 1 valence electron occupies the third energy level, and more specifically, it occupies the s orbit, okay? Now, here's something to think about, all right? Sodium is a metal. Do you remember what I told you about all metals with respect to losing or gaining electrons? Do all metals want to lose or gain electrons? You remember that? Okay, they want to lose, exactly, Skylar. But more importantly, if you forget, think about this, because in the third energy level, not only do I have the S and I got the P. So that means that in the third energy level, I need to add 7 more electrons. And from an energy perspective, that's not very efficient. Remember, nature is not going to do that much work. It's putting a lot of energy into the system. So it will be a lot easier from an energy perspective for sodium to lose that 1 electron that's hanging out there all by itself than it is to fill it up with 7 electrons, which will make it very, very unstable, by the way, okay? And so this is the electron configuration for the element sodium. When we lose that 1 electron, okay, guess what happens? That 1 electron goes away. It's the orbit's there, but that 1 electron is lost to something else, okay? And by losing that 1 electron, guess what happens to the charge of the ion of the sodium? It now becomes positive. Why? Because they had 11 electrons and then had 11 protons, right? 11 negatives, 11 positives. That's a net 0. Now it has 11 negatives, 11 positives and 10 negatives. Okay, what is our net? It's positive 1. And that is what happens to sodium by losing 1 electron. Now, how many valence electrons? We call this an ion. This is an ion now by losing that 1 electron. Can anybody tell me how many valence electrons does the ion have? Exactly, that magical 8, okay? Because now look at the ion, the sodium plus. It's got 8 electrons. 2 of them are in the S and 6 of them in the P. That's the magical 8, the octet. And sodium wants to become more stable, and it's stable by losing that 1 electron, okay? Become that ion. And so it's all about electrons, totally different property. This species with a 1 electron is extremely reactive. The metal itself is very reactive and very hazardous, okay? By losing 1 tiny electron that has an AMU of 0, remember how we defined it? Now we got something that's totally different. This is something you put in your French fries. This is sodium that's very crucial for the muscles to contract and push electrical signals in your body. Very crucial. Okay. And all that happened was this little tiny electron was lost. All right, let us continue with the next one. Let me clear this up. By using the same procedure, we're going to find we look for oxygen. Well, where's oxygen? We're going to find it on the periodic table. And sorry if it's kind of small here, but okay. So we got oxygen there. Okay. We realize that it is in the second energy level. Okay. And so the first energy level is full. So we can very quickly fill that up. 1s2, right? Oxygen has a total of, 8 electrons. The first two get filled up in the first energy level. We're now at the second energy level. We're going across the product table with lithium. We fill up the first two columns, okay? So that's 2s2. And then we shoot across into the yellow now, which are the p electrons. Notice where oxygen is. What column number is oxygen at in the yellow? What, if you count from the first yellow from left to right, what column is that? Okay, column 4. And guess what? 2p4. Okay. How many valence electrons does oxygen have? Exactly. And furthermore, if you forget that, what group number is oxygen in? So you go up to the top of the column, it's in group 6, Roman numeral 6, V1s, A, 6. That tells you I got 6 valence electrons. Remember, 8, and furthermore, everybody in that column has 6 valence electrons. Just like sodium, it was in group 1. Everybody in that column has 1 valence electron. Okay. Now, here's the $6 million question. Oxygen. Okay, do you remember if that is metal or non-metal? Okay, it is a non-metal. Okay, good. Now, is it going to gain electrons or lose electrons? It's going to gain them, exactly what that. And if it's going to gain electrons, how many do you think it's going to gain? 2. It is in group 6. Okay. It's in group 6. It has room for 2 more electrons. So again, think about it, energy state. We got 6 valence electrons, 2 in the S, 4 in the P, 6, total 6. Now, would it be easier to get rid of those 6 or just dump in 2 more? And honestly, it's going to be easier from an energy perspective to dump in 2 more, because when it does that, now the octet is fulfilled again. That driving force again is to get that octet done. So what would happen would be, if it gains 2 electrons, this becomes 2p6. And what do you think is the charge now for oxygen? Right, picking up 2 electrons, exactly. It is a -2. You got to be specific, correct? Because when we talk about charges, we have to be specific and say it's a positive or a negative charge. Okay. And so oxygen, being in group 6, has 6 valence electrons. Being a non-metal, it will gain 2 electrons. And guess what? With respect to nomenclature, when oxygen, the element, becomes now an ion. Remember, ions are nothing more than these elements, whichever one it is, that either gain or lose electrons. When you do that, they're now called ions. You may hear them as electrolytes. Okay, you're maybe more familiar with the term electrolytes. So when you're drinking stuff, sodium ion is an electrolyte, potassium another one. okay? Oxygen being a non-metal, and only for non-metals, when they become ions, the whole name changes. It goes from oxygen, and now in this state, we call it oxide. And so the term IDE is a flag for you to recognize that I'm dealing with the ion, okay? As compared to oxygen, which tells you I'm dealing with the element. Guess what? Chlorine will be the same thing. It will go from chlorine to chloride, and we'll have its example coming up. All right, so let me erase that. I'm introducing some things a little bit early, but you know, this is a good place to get you familiar with them. All right, now we got calcium. Okay, so we got to find it. So I go use my periodic table, and guess what? Here we go. Calcium sitting right there, number 20. I got 20 valence electrons to work with. Furthermore, it is in period 4, right? On this period. So what do I know right away? I can do this. Since it's here, it is right here. We go 1, 2, 3, and 4. I can very quickly, because it's period 2 and it's the second column, I can very quickly write 4s2. And I'm almost done here, because the rest is going to follow like the rest of them. We're going to go 1s2, that fills up the first column. Okay, 2s2, we're in the second energy level all the way across. Okay, and then 2p6, and then we go to the 3s2, 3p6, which 3p6 will put us right here, argon gas. And then we go around the horn, the 4th period, and we got 4s2. Okay, very quickly, just by its position on the periodic table. It's a little bit messy there. Let me take it off. But we go 1s2, 2s2, 2p6, 4s2, and then we go around the horn, or not yet, 3p6, around the horn to 4s2. Okay. How many valence electrons does calcium have? Exactly. Now, do you anticipate calcium to gain or lose electrons to become an ion? It would lose. Good. How many? It will lose 2, exactly. And what kind of charge would it have now? A +2, exactly. So if I were to get rid of those 2 valence electrons, which are in the 4th energy level, the electrons are no longer there, but the orbital's still there. They're just empty. And what happens is this calcium becomes an ion with a +2 ion. The valence shell now is full, 8 electrons. So by losing 2 electrons and becoming an ion, it's very stable now. Okay, very stable. Again, the driving force is these electrons. And so when you ingest calcium, you are ingesting not calcium metal, but the calcium ion. And that is the entity that is used there by your body to create bone and be used in bone structure. Okay. All right. And clear this, put it back up again. So that's the electron configuration of the element. I kind of introduced to you the ion part, and the ions are either a function of losing or gaining electrons. Okay. Now, everybody in calcium group, it's in group 2A, has 2 valence electrons. The difference is the energy level that those 2 valence electrons occupy. And if you were to look at magnesium, which is right above calcium, guess what? That would be 3s2, okay, for the valence electron. All right, now we're going to do chlorine. And we're going to first identify chlorine, and chlorine is sitting over here. on the far right, okay? It is in the third energy level, okay? And it is in group 7, which tells you there's going to be 7 valence electrons on there. So we can very quickly fill up the first energy level. 1s2, 2s2, 2p6, 3s2, 3p5, okay? It's in the 5th column. The 5th column of the P elements. So that tells you that P would be P5, okay? And being in the 3rd period, it has a total of 7 electrons, which is consistent with the Roman numeral for that column, VIIA, 7 valence electrons. Now, what do you think chlorine's going to do? You think it wants to get rid of 7 or just pick up 1? Exactly, gain 1. It will gain 1 because 2 reasons, right? It's a non-metal. Remember the non-metals and metals. Being a non-metal, it will gain electron. And the reason it's going to gain electron because by gaining electron, now the Bethe shell is happy and full, okay? They want to be like what we call a noble gas, and I'll explain that in a bit. And so if chlorine were to gain an electron, then this number becomes a 6, 3p6, and its charge now will be a -1 because it picked up 1 electron, okay? And that is a totally different ion, element, or species, I should say, compared to chlorine. Chlorine is a poisonous gas. Chloride, oh, notice, remember earlier I said oxygen, when it became a ion, we changed the name to oxide, okay? Chlorine as an element is chlorine, but the moment we gain an electron, become the ion, the name changes to chloride. So when you say sodium chloride, the chloride tells you you're dealing with the ion which has a negative charge. Only the non-metals get their name changed, okay? The metals don't change their name. Okay, so if I have a sodium, I have to be specific. Is it the sodium element or is it the sodium ion? I don't have to do that with the non-metals. When I say oxygen, that is the element. If I say oxide, that is the ion. Same is true for chlorine. That is the element. Chloride is the ion. And guess what? It's in group 7. So you got above chlorine, you got fluorine. Same thing's going to happen to it. Now you have fluoride. Fluoride is what you brush your teeth with. You know, you got fluoride in your toothpaste. And you have bromine that goes to bromide and iodine that goes to iodide. Okay. Oxygen went to oxide. Now, right below oxygen is sulfur. Okay. Same thing's going to happen to it. It's going to pick up 2 electrons. What do you think sulfur's name will be changed to? Sulfide, exactly. Nitrogen, the element nitrogen is in group 5. Okay, group 5, check your periodic table. It will pick up 3 electrons because it's a non-metal. Remember, the guys in group 4 are on the fence. They can either lose 4 or gain 4, and depends on the reaction conditions. But when you go 5 forward, up to 7, definitely they're going to gain electrons. So we got nitrogen. It becomes, name-wise, nitride with a -3 charge. Okay. All right. Don't want to get too far ahead with this. Really confusing. Now, here's the periodic table that will help you out. You can either use the periodic table on top or on the bottom. But notice the sequence. You're starting with hydrogen upper left corner. That's 1s1 for the electrons. Okay, 1s2 all the way across to helium. Now, the d electrons, though I stated they go D1 all the way to D10, in reality, they don't go sequentially. But for Chem 130, okay, We're not going to worry about that. We're just going to call it sequential. And so that means that right here will be 3D1 and just sequentially all the way across to 3D10. Same is true for the Fs, F1 to F14. Yes, they hop around. There's multiple reasons why that happens. But for us at K130, we'll just do sequential across the columns. If you notice now, when I was talking about the energy level for the D, here's number 21 sitting right here, SC. Right here, number 21 in the product table. Okay, it is in the 4th energy level, but D electrons don't come into play until you hit element number 21. And then the D orbits are 1 energy less. Down here, with respect to the S, 2 energy levels less. Yes, this for us at K130, that's not 6, but 5. 2 energy levels below. So this table kind of, you can see how the sequence is, right? With respect to orbital F. Yeah, I can do one, but I can tell you this, the likelihood of actually having to do one in a homework or exam is fairly low. But I can do one if you want. But let's take, I tell you what, let me continue with this, okay? Because there's more information I want to give you before I proceed, okay? And what I will do is I will put an email together and I would do an example of one of the F electrons, okay? Because like I said, the likelihood of actually having to do one in the lab or in the lab or the lecture, homework or exam is pretty low. Okay, all right, I'll do one and shoot it off to you. What's more important is to know how many electrons maximum I can put in the F orbit and how many in the D orbit. Now, if you proceed to go down and do Chem 1 and Chem 2 and get into organic and others, you're more likely going to ask to do that. Okay, but for Chem 130, it won't be necessary to get into the S. But at least understand what's happening there. Okay, so let me clear this up. So we know that noble gases. Now, what are the noble gases? Well, those are the elements in the far right of the periodic table. Okay, right here. The noble gases are these in group 8A. Okay. Now, with the exception of helium, all the noble gases have in their valence shell 8 electrons. And that is the most stable state that there is with respect to the electrons. So whatever the element can do to get 8 electrons around the orbit, it will do because that's stable. So either it's going to lose electrons like we talked about in the metals with respect to the metals, or it is going to gain electrons. But the ultimate goal is to have an electron configuration like the noble gas. So neon, argon, kryptons, xeon, these in here, they call them noble gases because they're very unreactive, okay? Now, for Chem 130, all noble gases are unreactive. But as a side note, when you get to the big elements, okay, it's feasible. But for us, it's unreactive. Just like gold. Gold is very unreactive. It's called the noble metal, okay? That's why gold can be buried for thousands of years. You take it out, it's just as shiny as the day it got buried. Okay, so noble gases on the far right column. Let me go back. And so they have full orbits, they're happy. So helium, remember, it doesn't have a, just, there's only got 2 electrons. So its noble gas configuration is 2. Okay, it's a duet rather than the octet. We talked about valence electrons. Again, valence electrons are the outermost shell, whereas the core electrons obviously make sense. They're the ones inside. Okay. And so if we look at phosphorus, its electron configuration is denoted here in this diagram. 1s2, 2s2, 2p6, 3s2, 3p3. Okay. It's got 5 valence electrons. Now, let me ask you a question here. Is phosphorus, based on what we talked about, do you think phosphorus is more likely to gain electrons or lose? What do you think? It will gain. Okay, point why? 2 points. Point number 1, it's a non-metal. Non-metals prefer to gain electrons. Okay. Second point, it's got 5 valence electrons. It's trying to get to the octet. And so, you know, losing 5 electrons from an energy perspective is a little bit tough as compared to just gaining 3. Okay. So it will gain 3 electrons because it has room for 3. It has room in the p orbit, the 3p, and fill that up. When that happens, guess what? The charge will be. If this were to gain 3 more electrons, what do you think the charge would be in phosphorus now? Want to say, what's the charge? On phosphorus when it gains a -3, exactly. Now, based on what I've talked about naming, what do you think happens to the name of phosphorus once it becomes an ion? Phosphite, exactly. And so now phosphorus becomes phosphite. And now you can distinguish, now you can start making compounds together because we talked about sodium. In fact, all of the elements in group 1 are going to lose an electron. And so they become positive charge. So I got sodium, potassium, lithium, and so on and so forth. Now I can start combining them with the negative counterpart, the chlorine, the chloride, the fluoride. So I got sodium chloride, sodium fluoride, sodium phosphide, but I'm going to have to add 3 phosphides. We'll get more about that in a while. But when I put them together, I want to put enough positives and negatives together so they cancel each other out to make a compound. And so that's where the subscripts come into play. So at this point, you got a couple hundred combinations of compounds that you can start working with. Okay, and if we proceed, we're going to learn that we can start making more. Okay, so in essence, we learn the letters. Okay, and now with the letters, we're starting to put them together to make words and different kinds of words. Yeah, so that's where we're at right now with respect to the chemistry, and then we're going to get into the chemical reactions based on that. All right, so the valence electrons out. We can write the electron configuration, or we can just find its position on the periodic table. We did chlorine earlier, right? So the number of valence electrons without even have to memorize anything. I mean, you're more than welcome to memorize all 118 elements and their electron configuration and how many electrons. But no, all you got to do is find its position on the periodic table. And yes, Skylar, that's correct. The number of valence electrons for chlorine is 7. And beryllium, we got to find it. Beryllium is element number 4. Okay, it is in the group Roman numeral 2A. So how many valence electrons for beryllium? 2. And then aluminum, you find aluminum, it is number 13. Okay, it is in group 3A. Okay, what do you think its number of valence electrons? 3, exactly. And so we can do that only for the A, Roman numeral A elements, okay? The first group, the first 2 columns, and then the 6 columns on the far left. The D elements, we can't predict how many electrons it has. They have variable charges, which brings me to the point, is this. With respect to ions, where'd it go? Make sure. Okay. With respect to ion formation, you will know 100% the charge on these elements that metals, are all metals that I put here. Everybody in group 1A, starting with lithium, I didn't include hydrogen, but it can have a plus. Hydrogen is very unique. Hydrogen, 1s1, first element. Remember the electron s orbit can handle 2. So hydrogen can can do 3 things. It can have 1 electron in this bed shell. It can lose that 1 electron, or it can gain 1 more electron to get a negative charge. But more on that later on. So everybody starting with lithium on down will lose 1 electron and always have a +1 charge to form an ion. Okay. Group 2, starting with beryllium in number 4, down to all the way down to Ra, they're in group 2. They have 2 valence electrons. They will always have a +2 charge. And then the other ones in the far right, aluminum, zinc, silver, Ag, and Cd, cadmium. Those that are circled there in red, those have constant charges. Aluminum always has a +3. Zinc always has a +2. Silver, which is Ag, always has a +1. And cadmium always has a +2. Okay, what does that mean? That means that all of the other metals, all these other metals here, can vary their charge. And so, for example, I wrote here an example of copper. Coppers can have 1 or 2 charges. It could be a copper +2 or a copper 1. Iron, Fe, which is iron, can be a +2 and a +3. And so those guys are variable, and we have to know more information to figure out which one it is. But the ones encircled, have 100% of the time a specific charge. I call those 16, the sweet 16. Okay. Why do you want to know that? Because in those cases, when we start naming compounds, here comes nomenclature. Those guys that are Roman numerals, excuse me, those that have a variable charge like copper 1 and copper 2, we use Roman numerals to designate which one we're working with. Copper 2 would be in parentheses II, capital II of Roman numeral. In parentheses, copper 1 would be in parentheses 1. Okay, and that's how we distinguish between copper 1, copper 2, and all the other charges that the other metals have. Because I noticed that some of you done a nomenclature or started that, and some of the places where you lost, didn't get it right, is using Roman numerals. And I know we haven't started that yet, and that's okay. You didn't do that in the test, but hopefully you're picking up on naming these compounds, and we're going to be naming them as we go along. Okay, nomenclature. We're going to have a whole chapter on nomenclature, but I will introduce naming as we progress. Okay, now let's go back here. All right, so those are the number of valence electrons for any of those A elements, the Roman numeral A. You can predict how many valence electrons they have based on their position. The D's and the S elements, we can't do that. And so here we can use this to aid you. Group 1A, 2A, 3A, et cetera, all the way across. That gives you the number of like valence electrons. Again, I can't overemphasize, only for the A electrons. Okay. Helium, as I stated, it doesn't have the 8, only has 2. Its rule is the duet. Okay, so we can find their position on periodic table. Strontium would have valence electrons. Bromine, Br, will have 7. Argon is a noble gas, would have 8. Silicon will have a +4. And sulfur, and a +4, will have 4 valence electrons. And sulfur will have 6 valence electrons. Okay? Just by finding their position on the periodic table. Now, first, the question here is, why do compounds or atoms make compounds? Okay? Why do they form a bond or an attraction? We're going to have 2 types of bonds. This is another aspect about chemistry that amazed me. Of all the billions of different chemical reactions that occur out there, there's only 2 types of compounds, bonds. There's a type of bond that actually share electrons. And then there is a type of bond that acts like magnets, and they attract each other. Okay, sure. I got my little magnets here. I can find it here. And so if I have, 2 magnets, they attract each other. Okay, and it's an electrostatic attraction. And there's no actual sharing of electrons. So that's one type of bond, is electrostatic attraction, which is made up mostly of a metal and a non-metal combination. And specifically, we call those ionic compounds. Now, the other ones that actually share, they have their own little name, and we'll get to those in a bit. All right. So right now, we're gonna start with ionic compounds. And that's dealing with the metal and a non-metal combination. Well, the driving force is the octet. We got to lose or gain electrons, so the new valence shell has that magical 8 number that it's looking for, those 8 electrons. And we talked about sodium here. That is the electron configuration of sodium: 1s2, 2s2, 2p6. Okay, and 3s1 is highlighted. The valence shell is highlighted. Okay, we talked about that it's a metal, so it's going to lose electrons, and by losing electrons, it's going to have now a positive charge, and we call that an ion. So any ion is an element that either has a positive charge or a negative charge. And that's because it either lost electrons or gained electrons. Okay? You might say, well, I don't see the charge. How does that come about? Think about it. Whether it is the element sodium or the ion sodium, what do those 2 have in common? What does a sodium element have in common with the sodium ion? Anybody tell me? Same number of protons. Remember, we can lose electrons or gain electrons, and for that matter, protons. Gain or lose those guys all day long, and we still have that element. But when we start losing protons, now we create a new element, and it's going to be a little bit tough, to lose a proton. But not that it's not possible, but there'll be a lot of energy involved with that. And so sodium element and sodium ion have in common the number of electrons. They got 11 protons, right? Where they differ is the number of electrons. And so I got 11 positive charges, and now I either have 11 negatives, which cancel the 11 positives, which gives us a neutral charge. Remember, all the elements have a neutral charge, okay? But when it becomes ion, in this case, losing 1, now I got 10 electrons. So now I got 11 positives, but only 10 negatives. So my net charge is a positive 1 charge. And its electron configuration now is 1s2, 2s2, 2p6. Now, whose electron configuration would that be? Anybody know? Whose electron configuration does this electron configuration resemble? Neon. Okay, if you look at your periodic table, sodium is number 11. Now, Neon is number 10. It is the noble gas behind it, right? And so here's something to remember. When the goal of the metals, well, all metals, but specifically 1 and 2, is when they lose those valence electrons, now they have the same number of electrons as the noble gas behind it. And so not only for sodium, but magnesium, a neighbor next, number 12. If number 12 is going to lose 2 electrons, when it loses those 2 electrons, it's going to have the number same valence electrons as noble gas. Okay. Now, this is important. It has not become neon. It has the same number of electrons as neon. It is what we call isoelectronic. Okay. For sodium to become neon, remember, it's got to lose a proton. They didn't lose a proton here. All right. So we we can look at the same thing. Look at sulfur. We know that sulfur has 16 protons and 16 electrons. Okay. Its electron configuration is written as follows: 1s2, 2s2, 2p6, 3s2, and 3p4. Point 1, it's a nonmetal, which says it's going to gain electrons. Point 2, it has 6 valence electrons. It will gain 2 electrons. Okay. And by gaining 2 electrons, now it has 16 protons and 18 electrons. I have a negative charge. So the net is a -2. All right. And its electron configuration, its valence shell, is written down right there. Now, whose electron configuration does that resemble? Argon. Okay, argon. Okay, and so whereas metals, by losing electrons, now have the same number of valence electrons as the noble gas behind it, nonmetals will have the same electron configuration as noble gases in front of it. So if you find sulfur in the periodic table, next its neighbor in front of it is chlorine, and after that is argon. Okay. Now I want you to, a little bit early, but I want you to think about this for a second. When it comes to radius, I want you to put your thinking caps on, okay? And if I look at the radius of these atoms, if I look at the sodium and the ion, based on what's happening to them, can somebody make a prediction? Can you make a prediction? A reasonable deduction of who is bigger in radius, treat it as a ball. Okay. So who do you think would be bigger, the sodium element or the sodium ion? The sodium element, that'll be correct. Now the ion, not quite. Think about it. What happened to the ion? It lost 1 energy level. Okay. And so we got the sodium element has 3 energy levels, 1, 2, 3. Now, when it became an ion, that outermost shell is lost. And so it's empty now. So the next one that's full is now in the 2nd energy level. So the sodium ion is smaller in diameter than the sodium element. So it lost size by losing electrons. What would you predict over here with the sodium, sulfur and sulfide? I forgot to mention that. Now there's become an ion. This is called sulfide. Okay. Can you make a prediction as who would be bigger, sulfur or sulfide? Sulfide would be bigger. That's correct, Skyler, because it gained 2 electrons. Those electrons have negative charge. It's got 6 of them out there, an outermost shell. Now I'm adding 2 with a negative charge. Negatives repel, right? And that whole thing is going to get bigger. So the ion of the negative charge will be bigger in diameter. Okay. And I also, you should be able to predict that if I were to compare sodium to potassium, who do you think is bigger in size, sodium or potassium, based on their position on the periodic table? Potassium would be bigger, and that'd be correct. Why? But potassium is in the 4th energy level, and sodium is in the 3rd energy level. So obviously, potassium is occupying more energy levels, a bigger onion, if you will. And I tend to think of these guys as, layers of an onion. All right, so that's good. We're picking up on trends, and we can make some predictions. Now, notice here, they're asking you to do electron configurations of these particular ones. Now, thing to notice here, these are ions. Why? Because they got a charge on them. Okay. One of the biggest mistakes that students do when they do the electron configuration, they don't really look at what they're looking at and they don't look at the problem, because there is a difference between potassium and potassium ion. There's a difference between nitrogen and the nitride, and there is a difference between magnesium element and magnesium ion. Okay. And the charges here tell you, oh, I got an ion, which means depending on the charge, I'm either going to take the parent. You can do one or two things. You can write the electron configuration for the element. And once knowing if it's a positive or negative, take out the valence shell by whatever number of electrons it has a charge, or add electrons. Okay. That may help you to distinguish the two, but it's important that you notice here, they got a charge in it. So we're talking about the ions. And that means you're either going to lose electrons or gain electrons in the electron configuration. And so if we look at potassium, 1s2, 2s2, 2p6, 3s2, 3p6. If it was the element, then it would be 4s1, correct? Nitrogen becomes nitride by gaining 3 electrons. And so now its new electron configuration is 1s2, 2s2, 2p6. It is like neon, okay? And magnesium also would be like neon with respect to the number of electrons, because its new electron configuration is 1s2, 2s2, 2p6, okay? Now, guess what? We can start making compounds. Let's do a quick one just to tell you how we're going to be doing this. We're going to put these two together, the potassium and the nitrite. And so I know that potassium has a +1 charge, and I know that the nitrite has a -3. Now, I got to put them together such that the charges cancel out. So how many positive potassiums do I need to cancel out the -3 of the nitrite? Exactly. I gotta need 3 of them. So I put them together. I put a 3 there, and that 3 becomes the subscript. So when I write the formula, it becomes K subscript N. Okay. K subscript N, and the name is potassium. And because we're dealing with the ion, this is not dealing with nitrogen. You are dealing with nitride. That's the ion. Okay. All right. So that's an introduction to, and now we do potassium, but you can do sodium, and I'm not going to introduce the positive, the +2 and -3 just yet. Takes a little bit of working through here, but just keep in mind, you can work through it. If I want to put these two together, the nitride and the potassium, keep in mind, I want to put them together such that the charges, enough of each to cancel out the charges, okay? And but I got a -3 and a +2, so I got to put them together in a special way, which is basically look for a common number. All right. I'll give you a hint there. We'll get more of that. No problem. Tell you what, it's 2:17. Let's take a quick break. All right, let's come back in 15. We'll call it what do we call it? Call it 2:30. Okay, I'm back. So the takeaway here is electron configuration for ions. Remember, you make sure you analyze the formula they gave you or the symbol for the element, and you recognize that you're dealing with an ion and not the element itself. So you're going to have to write it. The electron configuration will be like a noble gas. Okay. This deals with ionic charges, and we talked about this already. I've introduced it to you already, in that we know that in group 1, having one valence electron, it's a metal. It's going to lose that one valence electron, and therefore give you a positive charge, and therefore has electron configuration similar to the noble gas behind it. Similar with group 2A because of two valence electrons. And this is, again, for everybody in that particular group. This explains why these metals, these elements in the same group react very similar, is because they have the same number of valence electrons, okay? And when we get into the periodic table, you'll see that the gentleman who put this together, way back when, didn't have this information about, why do things react very similar? It's similar reactivity. That's because of the general the number of valence electrons that it had. All right, so we talked about this again. Group 1A will become a +1 ion. Group 2A will become a +2 ion, and the ones in plus and 3A will become +3 ions. Okay. Now, some people ask, well, is it +2 or 2+? It makes no difference. Tomato, same thing, right? As long as you got the charge up there to make a difference where you put it in. Same is true for -1 versus 1 negative, or whatever magnitude charge it is. Okay, so group 7, they want to be noble gases. Again, they're going to gain electrons. They want to be like noble gases. Excuse me, I said noble gases. They don't want to be noble gases. They want to be like noble gases, and therefore will gain electrons. Again, your non-metals, and non-metals gain electrons. Okay. Group 7A will become -1 charge. 6A will become plus a -2 charge, and group 5 will become a -3 charge ion. Okay. As I stated, metals lose electrons, and they become what we now call cations. I was using the term ions, whether it be negative or positive, but there is a term that specifically defines a positive ion, and those are called cations. Okay. Non-metals want to gain the electrons, and therefore its name becomes anion. The name of the ions are called anions, to distinguish between a negative and a positive charge. Now we know about group 4. Group 4, as I stated, starting with carbon, being in group 4, they're gonna either gain 4 or lose 4, or any combination thereof, depending on the reaction conditions. So their charge, they're on the fence. They can have anywhere from a total -4 all the way to a +4. And very interesting group about group 4. And of course, we know that group 8A, they're stable. Their stability is set because of the 8 valence electrons, with the exception of helium, okay? Because it's 2. So across the board, you see +1, +2, +3. Group 4, it's either going to be a plus or -4. And then we jump into the other side of the fence, if you will. We start with 3, -2, -1, and then the noble gases with a zero charge because they're not going to gain or lose electrons. All right. So to find out what kind of charge, you need 2 bits of information. One, recognize whether it is a metal or a non-metal, because that defines whether you lose or gain electrons. Once you know that, find it on the periodic table. We will be working with the A elements. We will be working with the D. Remember the D elements where it varies. We'll talk about those in a bit. So find it in the periodic table, find what group it is, and then that tells you what charge. So lithium is in group 1, and therefore will lose 1 electron because it's a metal. So it ends up with a +1. Magnesium is in group 2, 2A, having 2 valence electrons. Being a metal, it will lose 2 electrons. Sulfur is a non-metal, okay? And it is in group 6. Therefore, it will gain 2 electrons, having a -2 charge. Also, its name becomes sulfide. Nothing happened with lithium or magnesium with respect to their name. It remains lithium. However, now we say lithium ion or magnesium ion versus lithium atom or element and magnesium element or atom. Okay. Bromine is in group 7. It will pick up 1 electron, and also its name gets changed to bromide. Nitrogen, group 5, will gain 3 electrons because it is a nonmetal. And now its name will become nitride. And aluminum, group 3, it's a metal, 3 valence electrons. It will lose 3 electrons and have a +3 charge, okay? Now, the term I used before, being the same, I said isoelectronic, just simply means that when a metal or a non-metal loses or gains electrons, they're going to be isoelectronic with a noble gas, either a noble gas behind it, the previous noble gas, or the noble gas coming out, okay? Isoelectronic meaning iso meaning same, electronic meaning electrons. So what atom is isoelectronic with magnesium? Well, we find it in a periodic table. It's in group 3. It is going to lose 3. It's in, group 2A. Lose 2 electrons. It's in 3rd period. The noble gas before it is neon. Okay, and phosphorus will become +3. It is isoelectronic with argon. I cannot emphasize, please don't use the term, it becomes argon. It does not become argon. It is isoelectronic with argon, or it has the same number of electrons as argon, okay? All right, so you may see some tables, and you got calcium. Basically, you figure out the electron configuration for the calcium ion, okay? And that is the electron configuration for calcium ion. And here are the respective noble metals, noble gases that they're isoelectronic with. So calcium ion is isoelectronic with argon, and there's the electron configuration. Oxygen becomes oxide, and it's isoelectronic with neon. Chlorine becomes chloride as the ion, and it's isoelectronic with argon. And aluminum becomes aluminum ion. That's it. All right. You may see a table like this. We're looking at selenium, both the atom and the ion. Then you're looking at aluminum, in this case, aluminum 27 and aluminum ion. And so number of protons, well, we got to find where selenium is, and it's 34, right? Now, but in both cases, and let me highlight those so we could. In both cases, obviously, they're going to have the same number of protons, right? Because we did not change the element. Where they differ, obviously, is the number of electrons, where the element has 34, but the ion, selenide, has 36 because it gained 2 electrons. And the number of neutrons, like we did before, we take the mass number, subtract the number of protons, or the number of protons, and you get 44. Now, be careful, don't use the number of electrons to subtract, because look at here, if you do that, you're going to subtract 36, 78 minus 36, which is not going to give you the right number of neutrons, okay? So what remains constant for either the element or the ion is the number of protons and the number of neutrons. What changes only is the number of electrons, okay? Same is true here for aluminum. Neutrons and protons remain constant. The only change is the number of electrons. Okay. Congratulations. We are now done with chapter 5. And I will jump in to chapter 6, which is fairly short, 25, maybe 23, 25 slides, but take off 1, 2 for the beginning, and in the end, it tells you you're done. And so it won't take very long. Any questions on chapter 5? I will give an example of one of those F orbits and email it to you. Okay, and make note of that. Okay, chapter 6 deals with the periodic table. And we're going to make reference to it quite a bit. A lot of information on the periodic table. I've started to introduce you to it. How far back does the periodic table come? Well, there's a Russian scientist, Dmitry Mendeleev, way back in 1869. He put together a table of the known elements at the time. And he kind of put them in order based on their reactivity and how things reacted very similar. And so he came up with this particular table. And the fascinating thing about his work was in putting and organizing the elements in some type of a table that actually predicted elements, and that, because the table wasn't full. And so other scientists went around looking for these other elements, and sure enough, the elements were found. Now, the other aspect that's fascinating about this, keep in mind, 1869, not a lot of fancy, quote, modern equipment. The powers of observation, the powers of, good note keeping, and deduction allowed Mendeleev to come up with his periodic table. Okay. Well, it obviously is things that changed around. Another scientist, mostly what he did after the elements started coming in, start finding elements, and he put them in with respect to increasing atomic number. Okay, so this is what the periodic table, the modern periodic table is today, and what we utilize. Now, there's what's called the periodic law. The elements in the same column have similar properties. And now we know why, okay? Because a lot of these elements have the same number of valence electrons being in the same column, especially the ones, the A elements. And therefore, that's why they have similar properties, similar reactivities. Now, there are other tables. Now, notice how the table we see, we have those DF atoms. They're down at the bottom. Well, if you put them back in where they belong, your periodic table looks like so, okay? So it gets elongated. So what has been done, the green elements or the F block have been pulled out, and then the periodic table has been shrunk together, pushed together, so we can better visualize. Now, what they're trying to do, and they're trying to introduce a new numbering system on top. The periodic table that's been used up to this point had Roman numerals, either the A elements, or if you look at the D block, the D elements, they start with the letter B. So Roman numeral 1, 2, 3, B. The other ones are A. They're trying to change that and use a sequential numbers 1 through 18 to number the columns. Pros and cons about it. I obviously I prefer the Roman numerals because at a glance that tells me how many valence electrons I have. But you know, we'll see how that goes. They're still working and trying to figure out about that. There's been other periodic tables have been shown throughout history. Here's one, a circular one, okay, that puts the elements together. Pretty interesting. Okay. Another one is one that looks like this. And what this does, it actually predicts, if you look at this area up in here, there is a prediction of what are called these super ones up in here. They haven't been found yet. And so pros and cons, different ways to present the periodic table. You know, everybody has their own preference, and I think the preference that most people use to date is what we utilize as so. Now, as earlier we talked about Niels Bohr, and I introduced the idea of the S block, the D block, or the D elements, and so forth, P elements. And so that's based on the electron energy levels and how they're related to their position in the periodic table. Okay. Now, the horizontal row, which we introduce as an energy level, is called a period. Okay. And the vertical columns, the ones that have the Roman numerals on top, are called a group. Okay. Now, elements, as I stated, based on the periodic law, in the same group have very similar properties. Now, the ones in the Roman numerals A are named, also called the main group elements. And the B group are those are the ones that are the D block. Those are called transition metals. Transition metals. So we got main group elements as groups 1 through 8A, and then the ones that are labeled the B are transition metals. Okay, so here the horizontal ones, horizontal energy levels are periods. You also see the term shells, energy levels, energy shells. Okay, and then the blue up and down columns are the same are thought groups. Okay, so far nothing exciting. Okay, now there's also specific names for groups. So everybody in group 1A, with the exception of hydrogen, and I put the arrow there obscuring hydrogen in 1A, okay, they are called the alkali metals. Alkali metals. The next group in 2A, they are called the alkaline earth metals. Now, it moves across the periodic table to group 7, starting with fluorine, chlorine, and so forth. Those have their own little name. Those are called halogens. I think most of you are familiar, may be familiar with halogens. Some vehicles now, most of the vehicle headlights are LED, but there are some halogen lamps out there, made up of one of these elements. And then obviously we know about the noble gases as in group A. So those are the four groups that have their own little special name for that particular group. Okay. Now, the D block, the ones in green, are called transition metals. Okay, they're the ones with the Roman numerals B. Now, the ones that come out, the F group, there's two rows there, two horizontal rows. They have their own little name too. You can see them on the far left. The name's called lanthanides and actinides. So we have the transition metals in green. The ones in gray are called the lanthanides and the actinides. Okay, and so the lanthanides are also called rare earth metals, starting with CE all the way across the LU. Rare earth metals, very expensive. A lot of those metals are used in electronics and they do special things. The actinides are the next group. All of them are radioactive, kind of hot to handle. In fact, 93 and above are man-made and a lot and radioactive, and they're created by knocking particles together to create new elements. Okay, so the periodic table, some of these groups have their own particular names. So we could be asked the question, we need an alkaline metal in the third period. And so we got to remember who the alkaline metal, which would be group 1A. And in the third period, which would have to be sodium. Okay. We name a halogen in the second period, where the halogens are the group 7A. That could be fluorine, chlorine, bromine, etc. But they want one in the second period, so that would be fluorine. Okay, and then noble gas, which is the last column in the fourth period, which you bring it down to good old krypton, something Superman's not crazy about. No, that Superman's not crazy about. Kryptonite, totally different. This is krypton. All right. We talked about who are metals, who's non-metals, and who are the metalloids. Okay. Again, this is just a rehash of some of the stuff we spoke about in the past. All right. So you really need to at a glance be able to determine who's a metal, who's a non-metal, mostly who's a metal and a non-metal. We're not going to do a lot of work with respect to metalloids, and that's a whole area of chemistry. Is pretty fascinating in itself. But we're going to be dealing with mostly metals and non-metals. I mentioned this already about the radius, the size of these atoms. And that's the distance from the nucleus to the valence shell electrons. Okay. Now, obviously, as you go down the periodic table, you already figured that out. I asked that question. The radius increases as you go down the periodic table, where in effect you're getting a bigger element, more electrons. Okay, you got to put them in their specific energy levels. And so as we go down the periodic table, we got more energy levels, bigger radius. Okay. From right to left, the radius increases. Okay, think about this for a second. You look at the periodic table, as you go from right to left, the radius increases. So, why is that? Okay, let's pull up the periodic table. Okay. And let me get one that's not all marked up here. So we know, as stated, that going down the periodic table, the radius gets bigger because we're going down, bigger radius, more energy levels. But if I go from left to right, the radius gets smaller. You know, you go right to left, they get bigger, left to right. Whichever you're more comfortable with. The fact is that I could have, let me draw a picture, for example, just a relative picture. So I can have a big radius over here, but when I come over here, they get smaller. Okay. And the thing is, well, why is that? Okay. It makes sense going down the product table, but when you go across, you're in the same period. What is changing? Think about that for a second. What is changing as you go from left to right? When you think about it, you're increasing the number of protons. Okay. And you're also increasing number of electrons as you go from left to right. And so let me I'll leave it at that. So you're increasing the number of protons. So if I compare, let's say sodium has 11 protons and 11 electrons with chlorine, okay, if I compare those two, and we go here, say sodium compared to chlorine. See, they're in the same energy level. So we can't say, okay, chlorine is smaller, because the trend is chlorine is smaller than sodium. And the question is, well, why is that? It makes sense going down the product table, but why going from left to right? Why is chlorine smaller? Well, the thing that's happening when you go from left to right is we have more protons as we go from left to right. So sodium has 11 protons and 11 electrons compared to chlorine that has 17 protons and 17 electrons. The effect is, think of it as, I'm going to bring my little magnet here. As we go across the periodic table, you know, I only have an electron and a proton. The attraction is whatever force that is. But as I go across the periodic table, I pick up more electrons and more protons. Okay. And so now I got all this force of more protons pulling in the electrons. So that is why when you go from left to right, the radius gets smaller, because the forces of the protons and electrons it's greater, because you're getting more protons, more electrons. And in fact, those guys are pulling those electrons tightly. And you think about this for a second. What does that imply? That the sodium is going to hold on to their one little electron much less than the chlorine. Okay, because the chlorine is smaller in diameter, so those outermost electrons are being pulled in tightly, whereas compared to sodium, not as tight. It's going to be an interesting thing to look at when we talk about another property down the road, but it's related to the electrons and the protons that are involved there. All right, where am I? Yep, there you go. So positive charge increases and the electrons are just simply pulled closer, so the atom actually gets smaller. And so we can use the snowman kind of picture to help you out to remember. Down the periodic table, we got a snowman. The bottom part of the snowman is larger in diameter, okay, compared to the head. And just take the snowman and tilt him over, knock him on the side. You can see here, if you go from left to right, again, the radius gets smaller and gets smaller because the number of protons and electrons increase, and that force is greater. This is a general picture of some diagrams of pictures of relative radius. And the general trend is that it gets smaller. Yes, there's some fluctuation here and there. Nothing's 100%, but the general trend you can see going down the product table, radius gets bigger, going left to right, radius gets smaller. Okay. So you may be asked the question, all right, who is larger with respect to radius? So we've got three elements here, selenium and beryllium and oxygen. Well, to answer that, we got to find them on the periodic table. Okay, so find them on the periodic table, which I listed there, and put a little circle around them so I know. And the first thing I noticed that everybody is in the same group. Okay, well, this is a no-brainer, right? Because we know that Te is much bigger because it's in a bigger energy level. Okay. Well, now let's look at magnesium, silicon, and sulfur. Well, we got to find them on the periodic table, and we found them here, the diagram below. We got magnesium in group 2, and then across the periodic table, you got silicon and sulfur. So where they're all in the same period, and so going from left to right, sulfur will be smaller, okay, which is the trend. But the question is why? And again, because sulfur has more protons and it's therefore pulling the electrons closer in, and therefore results in a smaller radius. Right. Check the course website. There are more, there's some other videos with respect to atomic size. All right. So do take a look at those. All right. Which brings us to this final, we're going to be done here fairly soon for this chapter. This is called ionization energy. Remember, I talked about ions. So this is what you're doing is you're making ions. And how that happens is this. The equation is given to you up here. The reaction, I should say. This is what we do when we write a chemical reaction. I'll introduce that to you now. We have an arrow here. Okay, this represents a process, either a chemical reaction, or it could even be a physical process. But to the left are the reactants, and to the right are the products, or whatever they may be. So what this is saying is we're taking sodium, we're going to do something to it to produce a sodium ion, and we're going to generate an electron. Okay, and so what the ionization energy is, it is a measure of the amount of energy necessary to remove an electron from an atom. Okay, that's important, from an atom. We're going to have another property here in a couple of slides that is going to look similar, but it's not similar. Okay, so think about this for a second now. Earlier I said to you, the metals tend to lose electrons. And third thing I said, the nonmetals tend to gain electrons. Now we went to the periodic table and we said, okay, down the periodic table, the radius got smaller. But across the periodic table, the radius from left to right, the radius got, did I say that right? Excuse me. Down the periodic table, the radius got bigger, okay? And across the periodic table from left to right, the radius of the atoms got smaller. And we explained it because there's more protons, more electrons, right? So they're holding on to the electrons very tightly. Plus, on the right side, they tend to be nonmetals. Right side of the periodic table. All right, so when I try to pull electrons away from these atoms, those guys that are holding on to electrons tightly is going to take more energy to take an electron out, as compared to those electrons that by default, they tend to lose electrons. They're going to give them up easier. So I could make a prediction and say that I can predict that the nonmetals would have a higher ionization energy than the metals, simply because nonmetals tend to gain electrons. They tend to be smaller, and they tend to hold on to the electrons tighter than metals, okay? So that's going across the periodic table. But what about down the periodic table? If they're in group 1, they all have the same number of valence electrons, right? And yes, what if I'm comparing, let's say, lithium with potassium? They're both metals, okay? And I make a prediction as to which one would be will have a higher ionization energy? And the answer is yes, right? How can I predict that? Well, let's look at the periodic table. Okay. If I look at and do a compare and contrast between lithium and potassium, yes, what they have in common is that they both have one valence electrons. That's why they're in group 1A. But the difference is this: potassium is bigger, okay, than lithium. So the interaction of that one valence electron for potassium is much less than the interaction of the nucleus and the valence electron for lithium. Why? Because that one electron for potassium is further away than lithium. And so, there's not much energy holding on to it when I compare these guys in the same group. So I can predict that the electron for potassium will be removed much easier than the electron from lithium, because lithium's electron is closer in and holds it a lot stronger than potassium's electron, okay? So ionization energy for potassium would be much less than for lithium, is my prediction, because of that. All right, so again, ionization is the energy required to remove an electron from a neutral atom, okay? And so ionization increases as we go up a group for the same reason I just explained. So going down the group, whichever way you want to look at it, tomato, tomato. As I go up the group, it increases, or as I go down the group, it decreases, whichever way you want to look at it, all right? And it's simply because those electrons in the bigger elements are further away. So it's going to take less energy to remove an electron. As we go from left to right, the ionization increases, okay? Because again, we're going into the realm of nonmetals. We're going into the realm of a smaller nucleus. And we're going into the realm of those electrons being held on tighter and a lot more powerful than the ones on the left, okay? And so if we look at the data, and we get this, and you say, oh my goodness, look at this. Well, let's just break it down very quickly. If we start right here on the far left, the first point, guess what that is? That is hydrogen, far left. Oh, let me change the color here. As we go, we start with hydrogen and we go across the periodic table, we got helium. Okay, so again, the trend is left to right. Hydrogen has I don't know, let me erase that so I can see it better. Hydrogen is about, I don't know, call it the 13.5 energy units, whereas helium almost has 25, almost twice that, okay? So that's the amount of energy required to remove an electron. Well, it makes sense because helium is a noble gas. It's holding on to its electron very tightly. It doesn't want to give it up as readily as hydrogen does, all right? And so the energy goes up. Well, we go helium, then go around the periodic table, we're at lithium. And guess what? We're down here now, where it's around 5. And as you go across the period, it goes all the way across, the energy goes up. Again, we get into neon, and it's very high, about 22 versus lithium, about 5. Again, because you got noble gases. So see the trend? And the general trend is I go back to this guy here, argon, that would be sodium, starting with sodium and so forth. Now, the trend eventually starts to the slope starts to flatten down. And it's really consistent with the periodic table, because as we go down and get bigger elements, we're down in the 7th period, the electrons that are further away they're further away. So they're going to be held onto much less than the smaller elements. So the general slope, eventually you're going to see no difference. You get into energy level 7, there's a very small slope. You know, there's a difference, but not drastic like first 3 or 4 rows. Okay. All right, so let me clear this. Oh. Okay, now the question here is which has a larger ionization energy and why? Okay, and so we look at the elements. We've got chlorine, aluminum, and magnesium. Now, the first thing you should notice here, you shouldn't even have to go to the periodic table. Why is that? Because chlorine, what's the difference between chlorine, aluminum, and magnesium? What's the immediate difference that you can see between those 3 elements? Or is there a difference? Are they the same type of element? No, not at all. Chlorine, aluminum is a nonmetal. Oh, no. Chlorine, thank you. Yes, you are correct. Chlorine is a nonmetal. Aluminum and magnesium are metals. What do we say about metals? They want to gain and lose electrons, okay? Metals tend to lose electrons, so they're going to give up their electrons very readily. They're going to do that anyway. Chlorine's a nonmetal, okay? So it's not going to give up its electron without a fight, and it's going to take energy, a lot of energy to knock it out. Plus, as we go across the periodic table, the radius gets smaller. And so being smaller, chlorine has a smaller radius, so those electrons are held even tighter to the nucleus. And so chlorine, being a nonmetal, wants to gain electrons and not lose them. So it would have the higher ionization energy. Now we got this group. They're all in the same group, okay? Going down the periodic table. And what can we predict here? Okay. Lithium, being the smaller of the same group, holds on to its electrons much tighter than the larger ones. And so it will have the larger ionization energy. Okay. Larger ionization energy. All right, so do watch. There's also Dr. Kim has her version of the ionization energy. Okay, more information for you. And finally, one last aspect, and this is a very important concept because we're going to use this quite a bit with respect to chemical compounds and their structures. And this is also the driving force of why reactions are possible, okay? Because what is called the electronegativity. What the electronegativity is first of all, we get a bonded pair, 2 elements that are bonded. And there it is a measure of one of the elements' affinity to draw those electrons that are bonded. Now, how can I draw this out? Let me do this. Okay. Let me do this. I'm going to take a very generic example. And I'm going to have bonded a letter A bonded to another letter A. Okay. And then I'm going to have a letter A bonded to a letter B. And what I mean bonded is I draw a line between the 2. That line represents a bond. And that is a bond with 2 electrons. There are 2 electrons in that bond. We're going to learn more about this later on, okay? And so Just think of this as a bond in which two electrons are being bonded between two different elements or two of the same elements. Each element here has an affinity to pull electrons onto itself. So EN, the electronegativity, is a measure of that affinity. Now, when we look at the periodic table, fluorine is the most electronegative element there. And so we use that as a benchmark to determine which flow of the electrons are going with respect to a bonded pair. And from left to right, it increases, and from the bottom up, it increases. Fluorine is our benchmark. So if I were to say compare the electronegativity of a bonded between, let's say, nitrogen and chlorine, the fact that nitrogen is closer to fluorine, remember that's our benchmark, okay? Nitrogen in a bond, which I denote as this, will tend to pull the electrons more so onto itself than carbon will. So nitrogen would have the higher electronegativity, okay, simply because between nitrogen and carbon, because from its relative position, it's closer to fluorine, okay? If it was just, say, carbon to fluorine, this is a no-brainer there. Fluorine is the most electronegative, so it's going to pull those electrons in that bond more so onto itself than anyone. But when we're comparing other ones, we use fluorine as our benchmark to determine which one of those other elements have more electronegativity. And this is going to put a big factor on the properties that we'll be dealing with later on, okay? So if I look at an example between two elements that are the same, case in point, diatomic molecules like hydrogen, chlorine gas, hydrogen gas, oxygen gas, they are both the same element. And so they are pulling that bond equally, okay? And what results in a special type of bond, we're not going to talk about now, but we will. And it results in properties of that molecule that are very unique to it. And it's all brought to you by the electronegativity of the two atoms bonded together. And if we look at an example, a general example, A and B, just by the virtue of if it's B, it's a totally different element. That means that the bond, that hyphen, that line there, is going to be pulled by one or the other more so, okay? And we're going to have a different kind of bond, which results in different properties of that compound. And those are related to electronegativity. And it's going to come back to us later on when we start working with molecules and talking about properties such that, you know, boiling point, something that's viscous and so forth. We have some other things. So this is electronegativity is the ability of an atom to attract those electrons that are bonded, okay? And think of it as a tug of war. In that example with A and A, that tug of war is equal. I got two people with, 200-pound people pulling on the rope equally, okay? But think the one for the A and B, maybe B is maybe a 400-pound person and a 200-pound person. Well, obviously, that's going to be an unequal pull in that bond of electrons, resulting in totally different properties. Okay. All right. So electronegativity, we're going to revisit again later on down the road, but it's very crucial with respect to properties of compounds. Noble gases, they don't have no electronegativity simply because, they don't form bonds. Okay. And so therefore there's no pulling of electrons. Here we're talking about electronegativity is a measure of the attraction of the electrons in a bonded pair. All right. Congratulations. 10 more chapters to go. Right, so we're done with 4 and 6. I did move the exam to give you a little more time to get ready for it. Okay, so next Tuesday, we'll jump into, obviously, into 7, 8, 9, get the other set going. So I may have to move those exams, and we'll see how it goes. Right? Maybe we'll keep it there. We'll see how it goes. I'll be gone this weekend. I'm going up north to get out of this crazy weather. So I may or may not have